Okay, so oscillations and periodic motion. What do you think of when you hear that? Some of you guys have already been talking. You're saying stuff about like healthcare and finances. And is there anything that could possibly be like physics related that you think of when you hear oscillations and periodic motion? Trunks.
Periodic motion. It sounds like stop, start, stop, start.
That's really smart. We're going to look at some sort of stop and starting today. Motion. That's awesome because the word motion is in there. Okay. So when we talk about periodic motion is a motion that repeats itself over and over and over again, okay? So periodic motion repeats over and over and over again. So it keeps repeating, okay? And yeah, like a clock, exactly. Exactly like a clock. Have you guys ever seen a yeah, Trunks, what's up?
I was saying that, does it have like a time period?
It does, and we're gonna get there. So good thought. It has a time period. But yeah, like a clock. Like, have you guys ever seen a grandfather clock where it has a little hang down and it?
Yeah.
That's periodic motion, okay? And this repetition that occurs, we call it a cycle. So this repeating over and over again, we consider it a cycle. Okay, and then Trunks mentioned it happening over a set amount of time. Does anybody know what we call this time? A period, yeah. Okay, when we talk about periodic motion, we have a period of time, okay? And a period is the time it takes to complete, how many cycles do you think? One cycle, yeah. It's the time to complete one cycle, okay? Only one. Yes, Trunks?
If it never stopped, at that point, wouldn't it be a perpetual motion, which is like impossible? Something that
could happen in a vacuum, but it's not going to happen in the real world. That makes sense. And we do focus on things in a vacuum, okay? In addition to period, let's think about it. What do you guys think the variable is for period? Capital T. Okay, it's a capital T. And since this deals with time, what do you think the unit is?
Seconds.
Perfect. It's going to be seconds, okay?
Oh, so this unit's seconds.
The unit is seconds. The variable is T. So if we're talking about a period, we'll represent it with a capital T, okay? The other thing that we're going to have when talking about periodic motion is frequency. What do you guys think frequency is?
Like waves of energy.
Yeah, so it has to do with like how often these things pass, right? So what it is the number of oscillations that occur per a unit of time, okay? So frequency, number of oscillations per unit time. So basically, like, how many times does this thing occur during 1 second? Okay, like the frequency of your heartbeat. How many times is your heartbeat during a second? Okay, do they usually tell you how many beats you have per second? What do they usually tell you?
Per minute.
Per minute, okay. But frequency, since we're dealing with periods and seconds and everything, we're going to be dealing with it in seconds. So our variable to represent frequency is going to look really familiar, okay? It's a fancy F like friction was. Does anybody think they know the unit for frequency? It is hertz. It is hertz. And that's just represented by an H and a Z. Okay? What we would consider the base unit for it, for instance, base unit is like seconds, meters, stuff like that, is actually an inverse second. An inverse second is a hertz. And what an inverse second is means like we end up with 1 over a second. So this is actually how we get hertz. This is what it represents. Okay? And the best way to see that this is what it represents is to look at one of our equations for frequency, okay? So the first two equations we're going to see today is that frequency is equal to 1 over period. And when I say the second equation we're going to see, it's just moving this around to get that if we have frequency and we want period, that a period is 1 over the frequency. Okay? So the frequency is the inverse of the period, and the period is the inverse of the frequency. No, those are the two equations we're starting with.
Yeah.
Yeah, that'd be too easy. It's not just only would be too easy, it wouldn't be fun enough. Okay, so think back to our power lab, right? You guys were walking up the stairs. Okay, so let's say you get to the top of the stairs. And when you get to the top of the stairs, you want to know what your heart rate is. So you've either got your fingers on your wrist or on your neck, wherever you prefer to take your heart rate. And you end up discovering that it is 82 beats per minute. So you've got 82 beats every 1 minute.
As an example.
This is an example, yeah. So if you have 82 beats per minute, how would we find the frequency of our heartbeat? Because we want our frequency in seconds, because this is physics and we like seconds, we don't like minutes. Yeah, you divide by 60 by doing your dimensional analysis and saying that 1 minute has 60 seconds. So what is the frequency of our heartbeats? How many heartbeats do we have every second? Yeah. What are the units?
Or beats per second.
Hertz. Beats per second would be hertz. Okay? Because our beats are oscillations. Okay? So the next thing I want to know is, what is the period of our heartbeat then? How would we find the period of our heartbeat? Okay, so can somebody tell me what the period of our heartbeat is?
0.77.
What are the units? Seconds. Good job. All right. Now we're going to take things up a notch. We're going to talk about simple harmonic motion, okay? Don't worry, I will put that on the board. So simple harmonic motion. Don't let the name fool you. I think it is, but my classes tend to not agree with me. And I don't want to write this every time, so if I talk about it anymore, I'm just going to call it SHM, or simple harmonic motion. Okay. So simple harmonic motion brings in a force, okay? It is going to occur when the force that's pushing or pulling an object back towards its equilibrium state is proportional to how far we are from equilibrium. So that means how hard this force is pushing or pulling has to do with how far away we are from equilibrium, basically. So the further we are away from equilibrium, the harder it will push or pull. The closer we are, it's not going to be pushing or pulling as hard. So I'll write that up on the board so you guys can sort of put that down. So simple harmonic motion occurs when the force pushing or pulling an object towards equilibrium. The equilibrium part is important, okay? The towards equilibrium is important. Okay, so occurs when the force pushing or pulling an object towards equilibrium is proportional to the displacement from equilibrium. So one more time, that means if we're really far away from equilibrium, is the force going to be pushing or pulling hard or soft? As we get closer, what's going to happen? It's going to get softer. It's not going to be pulling quite as hard. What we call this force is a restoring force. Why do you think we call it a restoring force? It works to restore the object back to equilibrium. Exactly, okay? So it's focused on bringing the object back to equilibrium. Bringing object to equilibrium. That's its goal. It wants to get that object to equilibrium. Because if you think about it, every object in the universe wants to be in equilibrium. Equilibrium is the happy place in science, okay? One of the equation we're going to use to represent this is called Hooke's law. And what Hooke's law is that our force is equal to K times X. What do you think the K stands for? What? The spring constant. What do you think the X stands for? Distance. Perfect. Okay, so we got the spring constant and distance. And for here, we are going to go into drawing a pretty extensive picture and sort of talking through some conceptual stuff. So make sure to pay attention and ask questions as we go if you get confused, okay?
What is the spring constant again?
Huh?
What is the spring constant? Like, what is
It's newtons per meter, and it's like basically how strong is the spring. So like if a spring, like think about the spring in your pin. That's a really strong spring, right?
Will it be given to us, or is it always the same?
It's not always the same. You guys have been dealing with spring constants for a while now. And remember, sometimes you'd have to solve for them. Like the spring constant is in elastic potential energy and all of that stuff. It's the same K that we've had the whole time.
I was just going to write it.
No, it's never been one constant number. It's always been, it's different based on the spring. But that spring, if its spring constant is 12, no matter what you do to that spring, its spring constant is going to stay 12. Okay, can I erase this?
Mm-hmm.
Awesome. What was that sound for?
A yawn.
Oh, that was... Okay. So for this conceptual explanation, we're going to be talking about the same spring. We're just going to be looking at different snapshots of it, okay? Does that make sense to everybody? Okay, so you are going to want to draw this with me. You are going to want to draw it, all right? So sometimes you guys are like, should I draw it? Yes. Good, you should. Okay, so we'll have situation A, B, C, D, and E. And we're basically going to be following a spring through simple harmonic motion, okay? So these are just lines, and we've got an A, B, C, D, and E next to them, okay? When we deal with simple harmonic motion, and since you guys saw a spring constant, we're going to be dealing with springs again, okay? So this is going to be the start of our cycle, and E will be the end of our cycle. Okay, so at the beginning, we are going to have our spring pulled past equilibrium, okay? We have it pulled as far as we can pull it, okay? We've got this object attached at the end, and we have it pulled out to the maximum distance we can stretch this to, all right? Imagine like you pulled your slinky out as far as it would go, okay? So like I said, we have this at its max distance, which means that while it's here, it is at its maximum positive distance, right? It's at its maximum positive x position. It's as far as we can pull it away. Okay? When we are at our maximum positive x position, think about the restoring force we just mentioned. Do you think the restoring force is strong here, weak here, or zero here? It's going to be strong. It's actually going to be the maximum restoring force, okay? Max restoring force. I'm going to put F with a little subscript of RES to show restoring. But my question for you is this the maximum restoring force going to be to the right, or is it going to be to the left?
Right.
Are you sure? It's going to be to the left, because do you think if I pulled it far away from equilibrium as it is that equilibrium is over here? Or is equilibrium going to be over here somewhere? Yeah, it's going to be to the left somewhere. So it's the maximum restoring force to the left. Okay? And the one other thing I want to make sure that you know whenever we're pulled to this maximum distance is what our velocity is. If you had to guess, what do you think the velocity is here? Yeah, why is it zero? Yeah, and it's a turning point, right? Because what's going to happen the second we let go? It's going to go the other direction, which means that it's reached zero here, and it's going to need to go back the other way. Okay, so far so good? Yes, Trunks?
What happens if you break the spring?
Then this end will come bouncing at you, and you should hope and shield your eyes and hope that you don't get your eye ripped out by a spring. Okay, so from here, the spring is going to start trying to reach what? Equilibrium. Okay. So right here, it's at equilibrium. And actually, really quick, since you guys told me the max restoring force is to the left, I'm going to draw in the restoring force here, just so we can see that it's present there.
So what is the box?
It's just an object that's attached to the spring.
Oh, okay.
Mm-hmm. All right, so now we're at equilibrium, okay? So just to let us keep up with visualization, I want to label this as max x down here. And then I'm going to label this as our equilibrium. Okay? So this was our maximum positive x position, and this is our equilibrium. Now, when we get to equilibrium, what's our position? Yep, zero. We always said that everything gets measured from equilibrium. So when we're at equilibrium, our x is equal to zero. What do you think our restoring force is? Yeah, why is it zero? Because it's already at equilibrium, and the restoring force's only goal is to get you to equilibrium. Okay? What do you think our velocity is here? It's not going to be a number. I need more of like an idea. Like, how fast do you think it's going? Do you think it's going like its absolute fastest? Do you think it's going like half of its possible fastness? What do you think it's doing?
It's going like less than half.
It's going max speed when it reaches there. It is going its absolute maximum speed at equilibrium, okay? Because think about it. If you let something go, right, it's going to start speeding up, but then it has to start slowing down to a stop. So once it reaches equilibrium, it's at its maximum speed, and after it passes equilibrium is going to be when it starts to slow back down. Does that sort of make sense to you guys? Okay, awesome. So then after it reaches equilibrium, what do you think is going to happen? It is going to keep going. Yeah, and you're right. It'll start to slow down. So now we're here. We've passed equilibrium. We've gone through it. This is going to be our maximum negative x position, okay? So here we are at max negative x position. Okay? When we're at our maximum negative x position, what do you think the restoring force is like? It's what?
Negative.
Not really. It is, once again, the maximum restoring force. But last time it was to the left. Which way is it now? To the right. So we have our maximum restoring force to the right, because now it's going to want to get back to equilibrium, which is to the right. And what do you think the velocity is here? 0. Because once it reaches here, this is the maximum x displacement it can go. So to the left, so once it hits here, it reaches 0. It's compressed as far as it can, and now it's going to try and go back. The restoring force is going to push it back now. So it was stretched, came back to equilibrium, started getting compressed. It finally reached a compression that makes it then go back. Good thought process there, Nyla. Okay, yeah, so the next one, like she said, is that now we're going to end up back at equilibrium. Because it compressed and now it got pushed forward. Everything here is going to be same as it was last time we were at equilibrium. Same. So x is 0, restoring force is 0. It's at its maximum speed. Okay? What do you think it goes after that?
And it repeats itself.
Yep. So once again, it's going to be same as last time it was at its maximum x position. And then it's just going to keep repeating over and over and over again.
Oh, that's the cycle.
Yeah, that's the cycle. This right here is one whole cycle. This right here would take place in one period. One period is when you go from where you started, and then at the end, you end up in the same place.
Oh.
So this is one cycle. This would take one period to complete. Okay?
Springs, though?
Huh?
This is only for springs, though?
No, this is any kind of wave, but we're just representing it with springs right now.
Oh, okay.
Wow.
All right, so we get to build on this some more, okay? Yesterday, during Paul Hewitt, this is a wave, but he was representing waves like this, right?
Yeah.
Okay. And he showed that this middle portion right here is our what? It's our equilibrium, right? The middle line is our equilibrium. Rose, how do we find the amplitude? What is the amplitude?
It's only like the half above the equilibrium. Is that
It goes from equilibrium to the top, okay? That's our amplitude. So that's one way we can see our amplitude. The other way to see amplitude can be from equilibrium to the bottom of the wave, okay? Now, just to throw in some wave lingo to save myself if I end up using it without realizing it, this top part of the wave is called the crest, and this bottom part of the wave is called the trough. Okay? The crest and the trough. So just in case I reference the crest of the wave or the trough of the wave, the crest is the one that's at the top, the trough is the one that's at the bottom. Think about a pig trough. Or the crest of a wave. The crest of the wave is at the top, a pig trough. They eat out of that bottom thing, the trough, basically. Okay, now, this wave right here is the same thing as this, what we just drew. It's exactly the same. All you do is you take it and you turn it on its side. So, you guys see that?
Do you want us to draw that line?
It can probably help you, yeah.
Oh, man, that's gonna
So how you would find the amplitude of this would be from equilibrium to the maximum displacement. You see how it's the same thing? We just turned it on the side? Pretty cool, huh? Okay. Does anybody know from science, math or science, you might have learned in there too, what kind of wave this is, like what it's called? It's what? Sine. This is a sine wave, okay? A sine wave or a sine function. So if you were to ever graph a sine function, this is what it would look like. It's pre-calc. You're all supposed to be in pre-calc. Listen, I don't control what you're in. All I know is that if you're in my class, you're supposed to be in pre-calc right now. If you're not, that's the counselor's problem, not mine. Okay. All right. So there's another thing I want to point out here, okay? We said this takes place over one period, right? Okay. So what portion of a period exists between each one of these scenarios? From maximum to equilibrium, then equilibrium to maximum negative, from maximum negative back to equilibrium, and from equilibrium back to positive x. That's 1, 2, 3, 4 scenarios. How much of a period exists in each of those? Yeah, so how long it takes to complete one portion of the cycle is T over 4, okay? So that means that if you want to look at it over here because it's more clean, to get from here to here, T over 4. From equilibrium to this minimum, T over 4. From here to here, T over 4, and then to get back up to the top again, T over 4. So from crest to crest is one cycle, just like over here. You see how we went from crest to crest? One cycle, okay? That's okay. Who cares about spelling right? Do you guys have any questions about this?
What's the T line?
That's over 4.
Oh.
That's T over 4. A quarter of a period passes to get from crest to equilibrium, then another fourth passes from equilibrium to trough, then another fourth from trough to equilibrium, and then so on and so forth. Yes?
What does the A represent?
Amplitude. The A is amplitude. Can I start my erasing process so we can do an example? Alrighty, so we are going to focus on like a little car, frictionless, that is attached to a spring, okay? It's going across the table. It completes an entire oscillation every 2.4 seconds. So what does the 2.4 seconds represent, do you think? Which is the period. So our period is going to be 2.4 seconds here, okay? At t equals 0 seconds, we're going to release the car from rest at a distance of 0.10 meters, okay? So that means that we've got the cart and got little wheels because it's a cart. And if this is equilibrium right here, the cart is getting released right here, where x equals 0.10 meters. Okay, remember at equilibrium, what does x equal? 0 meters. Okay, so this is what it looks like at t equals 0 seconds. And it says we release it from rest. So what's our initial velocity over here? 0, right? Just like we said it would be at our maximum displacement. Yeah? Okay. So what we're faced with is we want to know the position of the cart at 0.6 seconds and at 0.2 seconds. So like x at 0.6 seconds and 1.2 seconds. Okay, and we know the whole period is 2.4 seconds. Okay, so let's think about this. When we release the cart, where is it going to be after its first quarter of a period passes? It's going to be at equilibrium, right? Yeah, I'll repeat that. Okay, so we said that to go from here, wherever we start, to equilibrium, it takes a quarter of the period, right? So I said after a quarter of the period has passed, where is the little car going to be? So you guys told me that it will be at equilibrium, right? And then after it goes to equilibrium, where is it going to be?
Negative distance.
Yeah, negative distance, okay? Here, that means we are at x equals negative 0.10 meters. Because it's going to go as far in the negative direction as it did in the positive direction. Okay? The only difference between this example and the one that I showed you on the board is we've got numbers now. Okay? Then after it goes there, the restoring force is going to push it where? Back to equilibrium. Perfect. And then where does it end up at the end? Back at 0.10. Okay. We are only asked, really, we want to know what the x is when we're at 0.6 and 1.2. So if we know the entire period is 2.4 seconds, how do we figure out which one of these occurs at 0.6 and which occurs at 1.2?
Divide 2.4 by 4.
If we divide 2.4 by 4. Okay, if we divide 2.4 by 4, what do we get?
0.6.
Okay, so that means that here we're at 0 seconds. Then at this next position, we'll be at 0.6. Then what's 0.6 plus 0.6? 1.2. What happens when we add another? 1.8. And then finally, we end at 2.4 to see this whole cycle take place just like it said it would, okay? We were asked for 0.6 and 1.2 seconds. So where are we at 0.6 seconds? Yeah, we're at 0. We're at equilibrium. Where are we at 1.2 seconds?
Negative distance.
Yeah, we're at the negative 0.10 meters. So when time is equal to 0.6 seconds, we'll be at equilibrium. And at 1.2, we'll be at negative 0.10. Yes, Trunks?
Is it x distance or displacement?
Well, it can be either, but right now we're talking about distance.
How do we get 0.?
Because if it were displacement, Trunks, wouldn't from here to here give us a displacement of 0?
Why'd you plug in the 4? And where did you put the 4?
Why did I plug in a 4?
Yeah.
Okay, you guys, listen up. Why we divided by 4, okay, is because previously, can you please be quiet? Previously, when I had the big example up here and we had the waves drawn, you guys pointed out to me that from here to here, and from here to here, here to here, it's not 4 cycles. This is all one cycle, but there's 4 segments within the cycle. So if the whole entire cycle from beginning to end is one period, that means that each of these is a quarter of that period. So it takes a quarter of the period to get from our maximum displacement to our equilibrium. Then it takes another quarter to get from equilibrium to our negative maximum displacement. Then another quarter of the period to get from there back to equilibrium. And then the last quarter of the period is getting from equilibrium back to our positive maximum x position. That's what you guys were talking about when we like circled them and we said, okay, so this is going to be a fourth of the period. So Trunks said, hey, if you divide it by 4, we'll figure out how much time passed between each of these transitions. Yes.
So equilibrium is always at 0.
Yes.
So is one ahead always at 0.10, and then one back always at 0.10?
No, because you could pull it further. So like, let's say, for instance, this started out at 0.672.
Oh, so they'll tell you that number in the problem?
Or that'll be what you're asked to solve for, given other things. But yeah, if that's 0.672, this would be negative 0.672. You're going to go the same distance you go in the positive x, that maximum, is going to be the same as your negative max. It's the same displacement from equilibrium. Rose?
I was just gonna ask, like, is every problem gonna be like this, where you have to draw like the whole like screen and everything?
Well, I know for a fact none of you are going to draw the pictures like you should. Maybe like 2 of you. So to answer your question, you probably should draw pictures for all of them, but you're not going to, and then you're going to get confused, and you're going to be confused why you're confused. And then you're going to come to me, and then I'm going to be like, why didn't you draw the picture?
Could we just draw the sign?
If that makes sense to you, yeah. That's still a picture, though.
It's not always going to be T over 4, is it? Or is it always going to be T over 4?
We're not there yet. Okay, do you guys have any more questions about this one before we keep on going?
So those also be compressed to start off with instead of.
It could be compressed instead, yes. So if we could have started compressed, and then it would have gone compressed to equilibrium to maximum positive, back to equilibrium, and so on and so forth. Okay, hush. I got a question, you guys. What's the amplitude of this wave? No, what's the amplitude of this wave? 0.10, because from equilibrium to our crest and trough, it's 0.10, okay? What's from equilibrium to our maximum displacement? That's how we get amplitude, and it goes a total of 0.10. What is the speed of this cart when we are right here at our maximum negative displacement at 1.2 seconds? What's the velocity? 0. Good. All right. That was the last question I had for you about these. So we're going to keep going to another example, okay? So can I erase this?
So basically the amplitude would be like the highest, like where you start from.
It's equilibrium to the highest. Yeah. That's why when I drew it over here, we had it like this. And then we said, okay, this is equilibrium. So amplitude is from equilibrium to the height. Yeah. So that's amplitude. And this is amplitude because these two heights are supposed to be the same. This is just the positive, and this is the negative.
Okay, but does that mean that height is?
Are you sure?
I don't know how to ask. I don't know how to ask it.
How about I'll keep that right there, so if you think about it, we can come back to it, okay?
Okay.
Okay. So we are going to deal with another mass moving back and forth in simple harmonic motion, okay? This time we're given the amplitude as 0.25 meters. And we're told that there's a period of 1.2 seconds. We want to know the distance traveled after we have gone a total time of 2.4 seconds. Okay, so to draw this in right side up waves, because it might make a little bit more sense. And we are just going to start out there, yeah. So we start out. Okay. Equilibrium. Okay, so how much time did we say occurs from here to here in one cycle? 1.2 seconds, right? How many seconds does it say we want to know the distance due to, though? 2.4. Okay, how many periods is that?
2.
Okay, so that's 2 periods. So should we be able to find how far it goes in one period in order and then just multiply by 2?
Yeah.
Okay, so let's say we start off right here. If we start out right here, what position are we at? 0.25, right?
Yeah.
Okay, then we come here, what position are we at?
0.
0. Okay, then we come here, what position are we at?
-0.2.
Then we come here, what position are we at? Then we come here, what position are we at? Okay, is that a whole cycle? Okay, so how far did I go from here to here? Yeah. How far did I go when I was going from 0 to negative 0.25? Just 0.25, you guys. This is just distance, not displacement. How far did I go when I was going from negative 0.25 to 0? And then finally, how far did I go from 0 to 0.25? Okay, so I went 0.25, then 0.25, then 0.25, then 0.25. If I add all of those together, how far did I go? Okay, and that was in 1.2 seconds, right? So how far would I have gone in 2.4 seconds? 2 meters. So the answer is 2 meters.
Wait.
That actually makes sense.
Oh.
Yeah, I can go over it again.
Why did you do the minus 1.2 and minus?
I didn't, though. That's me saying that in 1 meter, in 1.2 seconds, we've gone 1 meters.
Oh.
It's like a hyphen between them, so you can tell that they're connected.
So, the middle one, that's equilibrium.
Yes, that's equilibrium.
So equilibrium to the bottom, that's 0.5, right? And then equilibrium top.
Yeah.
So you're just adding the inside together?
Yeah, because see, when we go through a cycle, we start at one place, and then we go to equilibrium. So that's one portion, and that's how far we went. Then once we reach equilibrium, we're going to go past equilibrium another 0.25. Then once we've gone past equilibrium to another 0.25, we want to go back towards equilibrium, and that'll cover another 0.25. And then once we get to equilibrium, our goal is to get back to where we started, which is back at 0.25. So we would have traveled another 0.25. Because the whole cycle just occurs from where you start, and then the end is when you are in the exact same position you started in. So for instance, if for some reason we started at negative 0.25, it would go from there to the bottom of the next one. Or if we started at equilibrium, it would go from one equilibrium to another equilibrium, and so on and so forth. Okay, so we said that after one period was covered of 1.2 seconds, that we traveled a total of 1 meter. We were asked how far did we travel after 2.4 seconds, which is 2 periods. So we said, okay, well, if we do 1 meter in 1 period, we must do 2 meters in 2 periods.
That's what I was thinking. No, divide the 2.4
Oh, yeah.
by 2.
Gives you 1.2. Okay, can I erase it?
Yeah.
Okay.
Yeah, that makes more
And then we divide it.
Yeah, doing
That's
that
how
graph
I
would make a
yeah,
lot
the up
more
and
sense.
down way makes a lot.
Yeah, but the thing is, you guys aren't always going to be presented it in that way. So you need to know both.
Change it up.
Okay. So, period. The only equation we've seen for period so far is that it's equal to 1 over what? Frequency, right?
Yeah.
That is not our only equation for period, because sometimes you need period and you're not given a frequency. Okay? So period is related to two other factors: mass and the spring constant. Okay? So it is related, the mass on a spring varies inversely with the spring constant, and it's going to vary directly with the mass. So the period is inverse with spring constant, direct with mass. That means, inversely means that if something gets bigger, like if the spring constant gets bigger, that the period is going to get smaller. Okay? It means they do the opposite. Inverse means opposite. So like I said, as the spring constant gets bigger, period gets smaller. What happens if the spring constant gets smaller? Period's going to get bigger, okay? Directly with mass means the bigger something is, the bigger the period it's going to have, okay? The way that we...
So it's like having a bigger spring that if you use more force against it, that it will use, that'll be quicker, sort of thing?
Sort of, yeah. Yeah. Because if it has a bigger spring constant, that means that like when you push into it, it pushes something back, it's going to do it faster because it's a stronger spring, okay? The way we look at this mathematically is that our period is equal to 2 pi times the square root of m over k. So remember that T is period, m is mass, and what's k? Spring constant, okay? And thankfully, since this is still period, we're still going to have the same unit of just seconds. These units work out to give us seconds. Evan, lift your mask up. All right. At least 10. Okay. So we've got a car of 0.22 kilograms, and it's attached to a spring. The spring has a spring constant of 12. What are the units for spring constant?
Newton meters.
Newtons per meter. There's a difference. And we want to know what's the period of its oscillation. Do you have to rearrange anything here for that? No, you're just going to plug it in. So it's going to be T equals 2 pi times the square root of the mass of 0.22 divided by 12. I can't not give you guys a hard time about that. It's just like the definition of you don't listen to me when I talk.
0.85.
Woo! Who agrees with Rose?
85.
What are the units?
Second.
Seconds. Bam. Perfect. Okay. So one more example, then I'll let you guys free for the day, okay? Deal?
Yeah.
Awesome. Okay. So this next example, we're going to have to rearrange the equation, which is why I want to do this example with you, because I know every time there's a square root symbol in there, we all get a little afraid of the equation, okay? So we're going to have a mass. No, we're not going to look at that one. We have a mass of 0.32 kilograms now, okay? And it's attached to a spring that's going to undergo simple harmonic motion. And we're told that it has a frequency of 1.6 hertz. We want to know what the spring constant is.
You say that time here, period.
Yeah, but first, before we do that, we're going to want to rearrange the equation to solve for k. Okay? So we're going to start out with that our period is equal to 2 pi square root of m over k. What's the first thing we need to do to try and get k alone? No, it's going to be getting rid of the 2 pi. Okay, Randy, now what do we want to do?
Get rid of the square root.
Now we're going to get rid of the square root. How do we get rid of the square root, though? Yep, we're going to square both sides, which will give us this. Then what do we do? If I multiply by m, I'm going to have m squared over here.
You multiply.
Would you divide? Would you multiply the k and then we would?
Yeah, we can do that. So what Nyla just recommended was saying, okay, t over 2 pi squared multiplied by k equals m. And then what do we do to get k alone? You would divide by the t2 pi squared to get k.
If I write this equation in my notes and like memorize the equation, will I still have to show the work of rearranging it?
I mean, I guess not, but that seems like more effort than you need to go through. It's easier to just rearrange it than memorize it. Okay, now we have everything to plug this in. The only thing you're not straightforward given is period, but we are given frequency. How do we get period from frequency? Yeah, 1 divided by 1.6. You guys, what's 1 divided by 1.6? You guys agree with her? Okay, do you think you can plug everything in? All right, do it and let me know what our spring constant is. What's your answer?
I got no 2 of 4.
I got 0.33.
Did you guys make sure to square?
Yeah.
I swear the
You got what?
31.8. Or 833.
That's the right answer.
What is it?
31.83 newtons per meter.